Imagine holding the entire mass of our sun in your hands, feeling it weigh as much as Mount Everest, the oceans, and every city on Earth combined, all compressed into something the size of a single sugar cube. Now imagine standing on the surface of an object where that impossible density is normal, where gravity is so strong it can bend atoms themselves, and where the laws of physics are pushed to their absolute breaking point. This is not science fiction, this is not a black hole, and this is not some distant fantasy. This is real. This is what exists inside a neutron star, one of the most extreme objects in the universe. And today, on Cosmic Horizon Hub, we are going inside it. A neutron star is born from death, but not just any death. The violent, spectacular death of a massive star. When a star far more massive than our Sun runs out of nuclear fuel, it can no longer fight gravity. The core collapses in a fraction of a second. Protons and electrons are crushed together to form neutrons, and the outer layers explode outward in a supernova so bright it can briefly outshine an entire galaxy. What remains is the core, a neutron star typically only about 20 kilometers across, yet more massive than the Sun itself. To understand just how extreme this is, imagine shrinking the Sun, which is 1.4 million kilometers wide, down to the size of a city. That is the level of compression we are talking about. Now let's ask the first dangerous question. What would it feel like to stand on a neutron star? The answer is simple and terrifying. You wouldn't feel anything, because you would be dead long before your brain could register the sensation. Gravity on a neutron star is about 200 billion times stronger than Earth's. If you were dropped feet first, your feet would be pulled down far harder than your head, stretching you into a thin strand of atoms in a process scientists call spaghettification. But unlike a black hole, this wouldn't happen near an event horizon. It would happen immediately, violently, and completely. Even light struggles to escape a neutron star. If you shone a flashlight upward from its surface, the light would lose energy climbing out of the gravitational well, becoming redder and dimmer, barely making it into space. Time itself slows down here. A clock on a neutron star ticks noticeably slower than one far away, a prediction of Einstein's general relativity confirmed by observations. Now let's peel back the surface and go deeper, layer by layer, like cutting into the densest cosmic onion ever created. The outermost layer of a neutron star is called the crust, but calling it a crust almost feels insulting because this is no ordinary solid. It is a lattice of atomic nuclei squeezed so tightly that electrons are forced to roam freely between them, creating something like an ultra-dense metal. Mountains can exist on this surface, but they are tiny, only a few millimeters high, because gravity crushes everything flat. Even the tallest mountain on a neutron star would look like a wrinkle on a bowling ball. As we descend deeper into the crust, the pressure becomes so immense that atoms begin to deform. Nuclei are squeezed closer and closer together until they start forming bizarre shapes that sound like they belong in a kitchen rather than in space. Scientists call this region nuclear pasta. There are shapes known as spaghetti, lasagna, and gnocchi, long strands, flat sheets, and clumps of nuclear matter. This is not a joke. These shapes arise because nuclear forces and electrical repulsion are fighting a delicate battle under extreme pressure. It is one of the strangest states of matter ever predicted, and it may play a role in how neutron stars cool and how they generate powerful magnetic fields. Now we cross a boundary that fundamentally changes everything. Below the crust lies the neutron star core. Here, individual atomic nuclei cease to exist. Protons and electrons have merged almost entirely into neutrons, creating a sea of neutrons packed together so tightly that a teaspoon of this material would weigh about 1 billion tons. Think about that. A spoonful. 1 billion tons. This density is comparable to that of an atomic nucleus extended over a city-sized object. At this point, matter is no longer behaving like anything we experience on Earth. The neutrons are so close that quantum effects dominate. They form a superfluid, a strange state of matter that flows without friction. Imagine a liquid that can climb walls, leak through microscopic cracks, and spin forever once set in motion. Inside neutron stars, this superfluid may rotate in vast vortices, storing angular momentum like a cosmic flywheel. And this leads us to one of the most fascinating observational clues we have about neutron star interiors: glitches. Some neutron stars, observed as pulsars, suddenly speed up their rotation by tiny amounts. These glitches are thought to occur when the superfluid core transfers angular momentum to the crust, like an invisible hand giving the star a slight spin boost. It is one of the few ways we can indirectly probe what's happening deep inside. But the mystery doesn't stop there. Go even deeper, and things become speculative, almost surreal. Scientists are not entirely sure what exists at the very center of a neutron star. One possibility is that the neutrons themselves break down into their constituent particles, quarks. This would create quark matter, a dense soup of up, down, and perhaps even strange quarks. If strange quarks are present, the core could be made of strange matter, a hypothetical substance that might be more stable than ordinary nuclear matter. Some theories even suggest that entire stars made of this material could exist, known as strange stars. Another possibility is even more exotic: the formation of hyperons, particles containing strange quarks, or the emergence of states of matter we haven't yet imagined. This is where modern physics reaches its limits. Our equations struggle. Our experiments cannot recreate these conditions, and we are left with educated guesses guided by observation and theory. And speaking of observation, neutron stars are anything but quiet. Many of them are pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams, and when they cross Earth, we detect precise pulses of radio waves, X-rays, or gamma rays. Some pulsars rotate hundreds of times per second, meaning the entire mass of the Sun is spinning faster than a kitchen blender. The magnetic fields involved are beyond comprehension. A typical neutron star has a magnetic field trillions of times stronger than Earth's. A special class called magnetars takes this to an extreme, with magnetic fields so strong they can crack the crust of the star itself, causing starquakes that release enormous bursts of gamma rays. If a magnetar were placed halfway to the moon, its magnetic field would wipe the data from every credit card on Earth. Stand too close, and it would tear atoms apart, not with gravity, but with magnetism. Now here's a twist that sounds like science fiction, but is grounded in real physics. Neutron stars are incredibly hot when they are born, with temperatures reaching billions of degrees. Yet despite this heat, their surfaces are solid. The pressure is so high that heat cannot melt the crust. Over time they cool, but they do so in strange ways. Neutrinos, nearly massless particles that barely interact with matter, carry energy away from the core, allowing neutron stars to cool faster than normal stars. Observing this cooling gives astronomers another rare glimpse into the star's interior physics. Let's ask another question. Could you actually see a neutron star if you were close to one? The answer is yes, but it would not look like a typical star. It would appear as a small, intensely bright sphere, possibly glowing blue-white from its heat, with extreme gravitational lensing bending the light around it. You could actually see more than half of its surface at once because gravity curves the paths of photons. The star would seem to wrap around itself, a visual echo of Einstein's relativity. And if it were a pulsar, you might see beams of radiation sweeping through space, invisible to your eyes but deadly nonetheless. Now let's talk numbers, because neutron stars are statistics made real. Mass between 1.1 and about 2.3 times that of the Sun. Radius around 10 to 14 kilometers. Surface gravity hundreds of billions of times Earth's. Rotation periods ranging from milliseconds to seconds. Magnetic fields up to 10 to the power of 15 Gauss. These are not just big numbers. They are numbers that redefine what we mean by matter, force, and stability. And yet, neutron stars are not eternal. They exist in a delicate balance. Add too much mass, perhaps by stealing matter from a companion star, and the neutron star can collapse further, becoming a black hole. In this way, neutron stars are cosmic tightrope walkers, balanced between existence and annihilation. They are the last stable form of matter, before gravity wins completely. So why do neutron stars matter to us? Because they are natural laboratories. They allow us to test physics under conditions impossible to replicate on Earth. They help us understand nuclear forces, quantum mechanics, and general relativity all at once. They are also sources of gravitational waves. When two neutron stars collide, they send ripples through spacetime itself, events we have now detected, confirming predictions made over a century ago. These collisions also forge heavy elements like gold and platinum, meaning the precious metals on Earth were likely born in neutron star mergers billions of years ago. That ring on your finger, that circuitry in your phone, Parts of it may have been created in the violent dance of two neutron stars tearing each other apart. And here is the final thought, the quiet twist at the end of this cosmic journey. Neutron stars are reminders that the universe does not care about our intuition. It does not care about what seems reasonable. It takes simple ingredients, gravity, particles, energy, and pushes them to extremes until reality itself becomes strange. Inside a neutron star, matter is packed to the edge of possibility. Time slows, space bends, and the familiar dissolves into the exotic. These objects are not just remnants of dead stars. They are monuments to the power of physics, standing silent in the dark, spinning, pulsing, waiting to be understood. If this journey inside a neutron star stretched your imagination, if it made you see the universe as a stranger and more fascinating place, then let us know in the comments what part amazed you the most. Don't forget to like this video if you enjoyed diving into the extremes of cosmic science, and subscribe to Cosmic Horizon Hub for more deep explorations into the universe. Because beyond every horizon, there is always another mystery waiting.